Hello everyone and welcome back. I'm Mahanur and today we will be continuing on with some more conceptual questions on kinematics. And today we will actually focus more on the graphs of kinematics and see how for different kinds of motion and for different kinds of moving objects, we will see how we can draw and interpret their distance time graphs and their corresponding velocity time graphs. This will basically prep us to better attempt more of these graph related questions when we encounter them in our past papers. So let's actually revert back to one example that I'm sure you're already familiar with. Last time you might remember that we had looked at Tufi's journey, who had started from, let's say, this kind of a starting point. He had then moved 1,000 meters forwards, like so, and then he had stopped and then moved 200 meters backwards. Now, last time we had just restricted ourselves to numerically evaluating the distance and displacement, right? But now let's change the question. Now, suppose I ask you to represent this motion on a distance time graph. How would we do this then? Well, it's just a matter of breaking down the descriptive diagram given above in a way that we can draw it graphically. So let's first draw our axes. You have distance on the y-axis and time on the x-axis. Start. Now, for the sake of simplicity, suppose that Tufi travels with constant speed during this entire motion, which is to say that he covers these 1,000 and 200 meters amounts of distances in equal intervals of time. So with this in mind, start. Now let's look back to our scenario. Now what I've marked here as O is my origin in the graphical sense. Here that quote-unquote origin would mean our starting point or our reference point. Let that be this vertical line that I've marked. I'll even label it as O. So graphically speaking, Tufi starts his motion from here, right? Now in some time duration, let that be up to this point, we find that Tufi has moved 1,000 meters towards the right. So let's mark that off here. So that would be our first point. And then Tufi moves 200 meters backwards. Now those 200 meters backwards is, that motion is being covered while standing on the 1,000-meter mark. So I have to measure the 200 meters covered backwards by starting from 1,000, going down 200 to land at 800 meters. So the next point would be drawn somewhere over here, knowing that some time duration will have passed. Now how do I connect them? Do I connect them in a curved fashion or in a straight line? Well, for the sake of brevity, suppose that Tufi travels with constant speed in both cases, going forwards and backwards. Here we'll recall that on a distance time graph, the gradient or the slope represents, specifically for a distance time graph, it represents speed. So if I want a graph line that represents constant speed, it has to be such that it has a constant slope, which would be a straight line. So a straight line drawn from 0 to 1,000 meters, and then a straight line going from 1,000 to 800 meters. And so here we have our first distance versus time graph. Now comes the next part. How do I represent this on a velocity time graph? Or on a velocity, how does this represent on a velocity time graph? Let us first sketch our axes. velocity on the y-axis, time on the x-axis. That's the 0 point. In this case, that's the point where the object is moving with 0 velocity. Now 2phi already starts off with some constant velocity. We can see that in this first portion. Since this is a constant value, we expect the same constant value of velocity in the same time interval, right? Since this value of velocity is pointed or directed towards the right, we'll give it a positive sign and draw it somehow or somewhere like this. The fact that it maintains the same constant value in this time duration it makes sense because we just claimed that 2phi is moving with constant velocity. Now comes the next part, where in the next time interval 2phi moves with yet another constant velocity value, but this time it's in the opposite direction. We know that for vectors like velocity, an opposite direction can be given in terms of a negative sign. So instead of placing this horizontal line above the x-axis, I'll actually place it below the x-axis, so somewhere like this. And this denotes the fact that not only is the observer, in this case 2phi, moving with a new value of velocity, but moreover 2phi is moving in the opposite direction, denoted by the fact that whatever this value of velocity is, it's now negative. Great. Now let's add another layer of complexity to this scenario. Let's actually take the same observer 2phi in the same regular kind of motion that we have already described, but let's add a caveat to this. Suppose that 2phi waits 10 seconds before moving backwards. Meaning, instead of abruptly going the 200 meters in reverse, he stands after having covered 1000 meters and stands there for about 10 seconds before going in the reverse direction. Now we ask the question, how do the graphs that we've already drawn change? Well, for this, let's look at each of them carefully. Let's first look at our distance time graph. We have distance on the y-axis and time on the x-axis. Now we have already covered and understood why is it that we have these straight lines going up first, when first covering the 1000 meters and then going downwards when covering the 200 meters in reverse, right? So because the first half of the motion is still the same, we expect the first half of this graph to be the same still. That is, 2phi starts his motion from his starting point 0 and then covers 1000 meters in some given time duration, and let's mark that off over here. And since this is being covered with a constant speed, we expect the slope of this graph to be one that's constant, and so it would be a straight line like this. Now comes the part where we have to show that 2phi has to wait 10 seconds. When we claim that 2phi is waiting, that basically means he's not moving. So for the 10 seconds that follow the point or the time at which 2phi lands at 1000 meters, there will be 10 seconds that will pass. And during this journey, during this time duration, 2phi will not move away from the 1000 meter mark. And so he will maintain that displacement. And so we have a horizontal line here. Now comes the final point where in the remaining time interval, 2phi goes back 200 meters to land at the 800 meter mark, and so the graph line would be ending somewhere here. And so we see that the main change that has occurred in our graph is that there is this new inclusion of this horizontal portion that wasn't there before. This horizontal line suggests that 2phi is stationary. Not only is he stationary, but he is standing 1,000 meters away from his starting point. Great. Now let's see how does this translate into our velocity time graph. Let's draw that next. Velocity time graph. Now for our velocity time graph, we'll have velocity on the y-axis, time on the x-axis. Now the first portion is the same. You still have constant velocity when covering the first 1,000 meters, and it's towards the right, so we give that a positive value of velocity, and it'll be a constant value up to the point where he reaches the 1,000 meters. Now comes the next 10 seconds where Tufi is stationary. When Tufi is stationary, that is to say his velocity is 0. For that duration, so from this starting point up to, let's say, these 10 seconds that I've marked here similarly, we find that Tufi does not move, and so his velocity will abruptly drop to 0 and then stay 0 during the next 10 seconds. And it's only once Tufi starts moving in reverse that we find a new value of velocity in the opposite direction, and so with a negative sign drawn horizontally here as well to represent a new constant value of velocity in the opposite direction. So here too we see that same new inclusion of this horizontal portion that wasn't there before, right? Now let's look at the next question. Suppose you have Dr. Sal and Tufi both standing on the starting line. You have Dr. Sal here and Tufi right here on the same starting line. Now suppose that by the time Tufi stops here with an initial velocity of 0, Dr. Sal is already in motion at a constant value of velocity at 10 meters per second, and he continues to move like this. Now Tufi is alarmed by this and wants to catch up to Dr. Sal. Maybe he has a few questions that he wants to ask. So Tufi wants to start catching up, and so he accelerates until they both reach the same checkpoint or the same finish line right here. Suppose here is Dr. Sal, who has reached this finish line with the same value of velocity as he had before, 10 meters per second, whereas Tufi, having accelerated from an initial velocity of 0 all the way to a final velocity of 30 meters per second. Now we wish to show this kind of overtaking of one another graphically, both on a distance time and a velocity time graph. So let's first draw that distance, or more specifically displacement time graph first. Here we have displacement on the y-axis, s, and then time on the x-axis. Now suppose the distance that they both have to cover between this starting and this finish line, suppose it's about 100 meters. So I'll mark those 100 meters over here. Now the red line I'll draw to represent Dr. Sal's motion, and the purple line I'll draw to represent Tufi's motion. Now when it comes to the 100 meters that Dr. Sal has to cover, he has to cover them from the starting point 0 all the way up to 100 meters. And let's suppose this has taken some time duration. Right? Now, because we have Dr. Sal moving with the same constant velocity of 10 meters per second, it makes sense that we'll have a constant velocity that must be represented here as well. We'll remind ourselves of the fact, and I'll write it here as well, that for a displacement time graph, the gradient or the slope represents velocity. And so, a constant value of velocity implies a constant gradient, which can be expressed using a straight line, like so. Let me draw this once again. There we go. Now let's do the same for Tufi. Now Tufi had to start from an initial velocity of 0 and then reach a final velocity of 30 meters per second. Suppose he has his own time that he's covering, and suppose that ending time for Tufi is perhaps somewhere over here. Now, Tufi also reaches and in fact covers the same 100 meters, but the catch here is that he has different velocities when he starts and especially when he ends. At the starting point at t equals to 0, he has an initial velocity of 0, which means at the very starting point, the gradient of the graph line should be 0. So it might be some horizontal line like this. Whereas by the time he has covered the 100 meters, his speed is 30 meters per second, which is obviously greater than Dr. Sal's own speed. So whatever graph line I draw at the last time limit, it must be steeper than the graph line that I drew for Dr. Sal. So somewhere like this. Now the only way I could connect these different gradients with one another such that it's a smooth line is if I join them through a curve. So the kind of graph line I could draw would be this. Great. So we have a straight line for Dr. Sal because he is moving with constant velocity. And we have a curve for Tufi because he is moving with acceleration, meaning his speed or his velocity is definitely changing. Great. Now let's see how we can represent this on a velocity time graph. Now here I'll have velocity on the y-axis and time on the x-axis. Now this is very straightforward to draw for Dr. Sal because he maintains the same constant value of 10 meters per second throughout his journey. So somewhere over here, let's say, his velocity for Dr. Sal, is 10 meters per second and is maintained at that value throughout the end. Now let's see how we can draw things out for Tufi. Now for Tufi, his velocity is actually changing from 0 to a value of 30 meters per second during his journey. And suppose that this change in velocity or this acceleration is occurring in a constant fashion. Let's assume this for the sake of brevity. In which case, we remind ourselves that for a velocity time graph, the slope or the gradient represents acceleration. So if I wish to express constant acceleration graphically, I'd have to draw a graph line with a slope or a gradient in itself that's constant, which would be once again a straight line. So from here, let me sketch that again, like so. Great. If we look at this intersection point, I ask you a simple question. What does this mean physically? Give this video a pause and think about what this intersection point could mean. Well, any guesses? Well, it turns out that this point shows that for some point, at some point in time, both Dr. Sal and Tufi have the same Well, any guesses? Let's break this down graphically first and then figure out what a physical interpretation is. We can see here that these two graph lines are intersecting, meaning their coordinates are the same over here. Now on the x-axis we have some value of time t, and on the y-axis we have the same value of speed or velocity, which is 10 meters per second. Now what this means physically is that at this point in time t, at time t, Tufi and Dr. Sal both share the same velocity. Specifically, the same 10 meters per second worth of velocity. So on a velocity time graph, it's very easy to physically interpret what it means for two graph lines to intersect. All that means is that at that point in time, both moving objects, in our case it's Tufi and Dr. Sal, have the same velocity. Great. At this stage now, I hope that you're familiar and getting more comfortable with seeing how moving objects are presented and then seeing how you can interpret their motion in graphical forms, both for distance or displacement time graphs as well as speed or velocity time graphs. Now I believe you will be far more better equipped in attempting past paper questions where you have to deal with even more graphs. So do revise this thoroughly, and we'll soon enough encounter and learn how to attempt practice questions a lot more carefully. Thank you.